welcome to Module 41, in which we go a little bit more specific on the idea of representation learning and talk about embeddings specifically for particular modalities of data, specifically images and text, and we'll touch very, very briefly on graphs as well. So by the end of this module, you should be able to explain what an embedding is and how embeddings are used in different modalities. You ought to be able to compare embedding approaches for text, images, not really graphs, but to some extent graphs too, at a very, very high level for graphs, maybe a somewhat deeper for the other modalities. You ought to be able to use pre-trained embeddings for text and images to build simple downstream models or visualizations. We did this at the very end of Module 40 when we talked about representations. We had a pre-trained model on CFR10 using a convolutional neural network for images, and then we used that pre-trained embedding to build a simple additional model, a simple layer or a head we put on top of it in order to do predictions. You ought to be able to evaluate embedding quality using downstream tasks as a measure of that evaluation, and you ought to be able to identify basic risks and biases. Again, this is not too different from the module we just completed, but it's just a bit of more of the same and a bit more specifics along these ideas. So why are we doing embeddings? Well, many machine learning models don't operate on raw pixels or text or nodes or users or items or whatever the original data is. I mean, there's a big asterisk next to that. I mean, the input to our models are almost always going to be the raw data at some form, but there's usually this kind of a transformation stage at the beginning. Theoretically, we call this phi. Practically, we have these models that perform these transformations, but we're not going to be doing the training part or the distinguishing or the differentiation or whatever the task is directly on the original data space. We'll do some transformation on it first. That transformation usually involves taking the data X and representing it in d-dimensional vectors of real numbers, which we've called Z before. That's our representation. So a d-dimensional real vector is just a point in continuous space. And because it's a point in continuous space, we can apply geometric operations on those points, and some of our geometric intuitions can be brought to bear on this. I suppose that's the main message of Module 41, this module, compared to the previous more high-level module on representation learning. It's the idea that, well, these vectors, these representations Z, are points in space, and because they're points in space, we can do things with them. I mean, technically, we saw points in space in terms of PCA and LDA in the previous module, but we're just going to reinforce that in this one. So because we have points in space, we have similarity measures. So we have distances between points. We have angles between points. And again, these points in space, we know how to deal with points in space. We've been dealing with points in space in terms of our SVM models, in terms of our logistic regression models, and so on, so we know what to do with them. The big idea is we have this function we want to learn. We have objects, very generally. This can be representations in various forms in terms of the raw data, and we want to transform them into d-dimensional vectors. We want the geometry to represent semantics. Again, this is reinforcing an idea from the previous module, but if points are close to each other in space, they have to have some kind of similarity between them. We want them to have some kind of similarity between them. And what is that similarity? Well, it has to do something with the meaning of those points. Again, unfortunately to some extent, but also thankfully to some extent, what constitutes semantics is something that we don't get to measure too much. We can try to illuminate these neural networks to a great extent, but generally these massively parameterized models, the semantics or the meaning will be spread very broadly over the neural network. So it's very rarely very clean. But generally you get the idea. If two data points exist in the same, close to each other, there should be some similarity that carries some real world meaning between them. These relationships can be, for example, in text. Imagine if you want to learn something about the language of English or whatever the language you're dealing with is. Well, I mean, English isn't gendered as much as other Latin languages are. Like French, for example, there's a difference between la poubelle and le pont, for example. So the gender of a word would be encoded within the meaning of the word. The tense of a verb, if it's past tense or present tense, That would be encoded. What the topic is would be encoded somehow. The style of language, if it's formal or informal. All of these aspects, all of these relationships between words and these concepts would be encoded within the representations in space somehow. We'll get to this in a moment. So let's just go ahead and do our conceptual scaffolding. Remember from the representation learning, any way of turning raw data into a form that a model can work with effectively would be a form of representation learning. So bag of words vectors, pixels, spectrograms, which is an amazing topic, but one we don't have time to get into in this course. Handcrafted features of the type that I complained about. These are all forms of representations. Embeddings, specifically, are representations that lived in fixed dimensional vector space. So we're going to say we're going to have d dimensions and always d dimensions, and our embeddings will always be in these d-dimensional vector spaces. They're almost always learned, so embeddings are learned representations, and they tend to be very dense. So when you pass x into an encoder, the vector z in this d-dimensional space, every element of that space will carry a lot of information in it. So you're rarely going to have like a sparse representation in which you'll have zeros or not very much contribution from these dimensions. Like everything will be like information's packed into these embeddings. So here's a little definition, and here's our for all of our points x that we could possibly have in our data space. There needs to be a function that transforms it into an embedding in our d-dimensional vector space. There should be a similarity or distance notion. Sometimes this is provided explicitly, sometimes it's an implicit emergent property of our embedding, and we'll see that soon. But Euclidean distance, like the actual Euclidean distance between points, the cosine similarity between points, the dot product, which is intimately tied to cosine similarity, and so on, are all kind of ways in which we'll measure similarity or distance in embedding space. Here's just a little visualization of raw objects to embedding spaces. We have our raw objects. Our raw objects could be a series of words in text. They can be pixels representing images, or they can be graphs. So focusing on the first example, so this is a good example of a task in which we might have multiple modalities, and each of those modalities will have to be dealt with separately and together. So we want to have the modality of text to be embedded into a text space, a text representation. So here we have all these kind of blue dots represent, encodings of sentences, or at least phrases like we have here, into a vector space of meaning that in which how close together points are in space means that these two bits of text are related to one another somehow. So here we have, the labels might be a bit off here. I apologize for that, but like dog in a park is this dot up here, which I'm indicating. Cat on a mat is this point down here, which you can infer because it's the base of this arrow. And then the Toronto skyline is over here in the left area. And what I tried to convey here is that dog in a park and cat on a mat are more similar to each other, or they're similar to each other in some sense. They're in the same cluster compared to the Toronto skyline, which is a bit off to the side over here. So the encodings, the embeddings of each of these bits of text will map onto points in space in this little collection of blue dots over here. Each of these images, which can be transformed into vectors of pixels, can also be encoded into points in space. We did this in the CFAR example in the previous module, in worked example 2. All of these embeddings are going to be points in some space representing images, shown here as these orange squares. So this is like one embedding for the text, one embedding for the images. We'll talk a little bit later on about how sometimes you want to train these embeddings separately and together, because you want to have a mapping between the fact that a cat on a map maps better to this image of a cat than it does to this image of a dog or this image of a city skyline. So it's not just that every modality gets its own embedding, but often we want to have a embedding of mappings between modalities. just to wrap this up, it doesn't, we're more used in many situations we tend to see in courses like this. We're more used to seeing text and images, but social graphs, or any kind of graph really, also forms the basis for other kinds of representations. Here we have, I guess, a somewhat poorly drawn social graph in which we have vertices connected by edges, and the edges can be anything you can care about, like these user A and user B are both posting to the same community, or they're both posting the same kind of content or on the same kind of topics. So you have a lot of posts from user A, a lot of posts from user B, and you would embed them in a space. All of their posts would be embedded in spaces where user A's postings would all be close together, and because user B is similar to user A in some sense, maybe user B's embeddings would be similarly embedded in a similar space in the embedding space, the common vector space Z. So here's another anti-example, the idea of misleading embeddings. So imagine you download a black box text embedding model that's already been pre-trained. We did something like this again, and we're going to do it again by just like asking PyTorch, or in a few moments something called GenSim, to just download a model for us that other people have trained, and then we're going to use that pre-trained encoder for our own purposes. Hugging Face is a place that people tend to go to for bigger, more modern, more cutting-edge models a lot of the time than these kinds of libraries we've been using, but the same principle applies. You just pull down a massive model that was trained somehow by someone on something, and you want to use it. So you want to use it, in this case, to rank job applicants based on their cover letters. So you take the cover letter, you extract the text from that cover letter, you pass that text into this embedder, this encoder, which basically represents all of the words and all of the sentences in this cover letter as points in space. And then now this entire letter can be represented as one point in space. So there's a point in space that represents everything about that letter, magically somehow, but truthfully. And then you have another embedding somewhere else, another point, which represents your ideal candidate. Like you have someone you hired previously for this position, you have their CV, or you have their cover letter. So they have a point in space, this perfect person that you've hired previously. You have this new applicant over here as another point in space, and you can measure the distance between these 2 points in cover letter space or in text space somehow. Actually, it's more like text space really right now, because we're dealing with this black box model that's just good at embedding text, but not necessarily good at embedding cover letter text specifically or differentiating cover letter text specifically. So we have our best, candidate, best person we've hired previously. We find the 5 points that are closest to it, representing 5 different cover letters from 5 different people, and we're going to hire the 5 people, the k equals 5 people who are closest to that that applicant that we hired previously. So it sounds reasonable, and sometimes that kind of approach could be fine as long as you do all kinds of checks on it, but there are also a lot of problems or potential problems, so you have to check for these problems. The first one is that the embedding model could encode historical biases of various types, so we don't know necessarily whether or not this model was trained on data from several decades ago, in which the incongruities between the genders or sexes or races or and so on were potentially even worse than they are today, or these biases were encoded in a way that wasn't sensitive to those specific demographics, so they weren't dealt with appropriately. So you're using a model that was trained on racist or sexist or data, so to speak. Similarity to past hires, so your criterion that you're using, just get the 5 points or the 5 applicants that are most similar to one I liked previously. If that previous hire was also hired because of inequalities in the system, you've done nothing more than reinforce those existing inequalities. Again, I'm just literally using these embeddings. I'm not doing any kind of extra learning from it, right? So this model could be a good general purpose model for most tasks, but you're still expected to do some training on the model afterwards by slapping on a head on top of the model. And if you don't do that, maybe it's not such a good model for cover letters specifically, like I alluded to a moment ago. So you're not doing any calibration. Similarities in this space are not really that meaningful. And there's other issues like protected attributes, they're proxies we just haven't dealt with. So the key lesson here is nicely structured embedding spaces, or even an embedding space that you've read a ton about and it tends to do really well generally. It doesn't mean it's fair, and it doesn't mean it's really suited for your task, so you need to still be a smart person and apply the regular mitigations. So again, I kind of framed embeddings as functions a few moments ago. So at a high level, you have a function that takes a token or a sentence or a full document, and then produces a d-dimensional representation in text space. Similarly, you could pass a pixel array as X and produce a transformation into image space, or a node adjacency matrix, apply it to a function that's good on graphs and produce a embedding in graph space. So each of these functions often come from a neural network. Neural networks are fantastic encoders. And over the years, various different kinds of neural networks have produced specialized embeddings in different modalities. So we're going to see word-to-vec and glove a little bit today in this module. Later on, we're going to see BERT and sentence transformers as we get deeper and deeper into deeper models. Convolutional neural networks and other kinds of vision transformer and vision transformers have been very good encoders. They've performed the function of producing image representations very well over the years. And we're going to cite DeepWalk and Node2Vec soon enough. There's graph neural networks, which, as the name suggests, are very good at producing representations given graphs. So one of the key design choices you need to make is like, what structure do you want to preserve? Do you care about locality and neighborhoods? Do you care about global distances? Do you care about like local node communities? Do you care about temporal order? Like you care about surely temporal order like in text. Like text is my area of primary interest, and we could spend a lot more time talking about how important word order is in language, but maybe we'll come back to that a little bit later with transformer neural networks. And then, what objective do you want to use? Are you just going to predict words in context? Like, are you going to predict the next word in a sequence given previous words? Are you going to classify image as dogs or cats or airplanes? And so on. So you need to think, obviously, about these primary questions initially. How do you measure similarity? So I alluded to this a moment ago. I don't want to spend too much time on this because you already know these functions. The Euclidean distance is just basically the 2 norm that tells you how far apart 2 points are in space. So this is the Euclidean distance in Euclidean space. Cosine similarity is the dot product of the 2 vectors. Basically tells you something about the difference in the angle between them. Actually, this is literally the dot product, which is from below. You basically take you take the transpose of one, multiply it by the other. This gives you a scalar value, which is basically the cosine function, like the angle between these 2 vectors, and then you normalize by the lengths of these vectors. So u and v aren't necessarily unit vectors, so you normalize by their lengths. So if v is very long or very short, for example, this has an effect on the cosine similarity. Why do you care about cosine? So this is more or less because often we care about the direction more than the magnitude of these vectors, or sometimes these vectors are actually already represented as unit vectors. But in high dimensions, raw distances can be less informative. So if you have like very dimensional, highly dimensional space, like embeddings, the dimension d is like 300, 400, 500, or thousands or millions increasingly. Because of something like the cursive dimensionality, the distances don't matter so much, but the angles between points matter a lot more. So cosine is a standard way of comparing how far apart points are. You can compare a couple of these things also, right? You have a lot of tools in your tool belt, so why do you have to choose Euclidean or cosine? Why not use both? In fact, I've seen instances where some PhD students in other universities didn't consider that they could have used one or the other, or didn't have a good reason to use one or the other. So, if you have time and you have the resources and the wherewithal, just go ahead and use both measures and see what works best for your purposes. If your embeddings are going to be used with something like k-nearest neighbors or clustering, which again, these are topics which I assume you've seen in other courses already, you're going to want to choose a similarity measure that's consistent with how they're going to be trained, right? So if you're going to be doing something like k-nearest neighbors, then maybe the Euclidean distance is going to be more relevant to you. If you're going to be doing something like a classification task using text embeddings, cosines or dot products are much more common. So just very briefly, again, this is something you don't necessarily necessarily need to know going forward, but there's going to be very popular text embeddings like word2vec. These are trained with a contrastive objective. So we want to know which words, we want words, representations to be similar to their context words and dissimilar to random words. So the idea is you have a target word W that you're trying to predict, and you have some context word C, and you have the representations V sub W for target word W, you have V sub C, which is the embedding for context word C. Then you can form this the skipgram with negative sampling, which will look like this. It's the log of the sigmoid of the dot vector, so the similarity between these two embeddings, plus 1 to the power of k of negative samples, so like words that are not the target word, the similarity between them. So you take the negative dot product between the word that you're trying to predict and all of these words you're definitely trying not to predict, which is where the negative sampling comes from. And you take the similarity of those, you pass those through the sigmoid. We do logarithms of each of these things, and then you basically try to get the expected, negative similarity between the words you're trying to predict and all of these words you're definitely trying not to predict. This function, because you're kind of penalizing the similarity between target words and randomly sampled negative words. We could sample k of them, and it'll dissuade similarity of your embedding to be your true embedding to be similar to these bad embeddings. So it'll push them apart because of this term, and because you want to optimize or encourage the embeddings of your target words W and your context words, it'll this term sort of is used for promoting that similarity. So a target word should be similar to the context in which it appears, but it should be very different from other random words that I might like randomly put there as confounds or noise. Again, this is something that's much more related to text, which you don't have much time for, but hopefully you get the primary idea of this, which is I want to learn an embedding where I want to separate and maneuver my vectors V, my embeddings, into spaces that carry useful meaning, first term, and discourages or dissuades bad or faulty connections, which I get from the second term. Skipgrams with negative sampling will learn embeddings where co-occurring words will have words that occur together, like they call it words of a feather flock together. Words that occur together, words that are similar in some sense, to have large dot products, and this will be shown to roughly factorize this shifted pointwise mutual information matrix. This is actually, I should cite this work. This is really just a curiosity. Don't worry about it, but this is just the theory that shows why this works as well as it does. But it's a good idea. I wanted to mention this just because we talked a moment ago about the objectives, the training objectives that we can apply to learn good embeddings, and this just emphasizes that we want to encourage good embeddings and we want to discourage bad embeddings, and we can put those two ideas into the same objective function, which we use for training. This is a training function. This is the objective. This is our loss. But the specifics of this, don't worry about it too much. So for text embeddings, there's sparse count-based representations that would take us back to like the early 2000s. So bag of words, term frequency, inverse document frequency, or TF-IDF, which are used to be super popular in computational linguistics, or n-grams, which are just sequences of n words side by side, and the statistics associated with them are like the old-fashioned way of representing words, contexts. They still work very well. So TF-IDF, I keep on saying even in very modern research papers. N-grams also similarly come up a lot. So just because something is old doesn't mean doesn't mean you don't need to learn it. It's always good to learn as much as you can, but these produce high dimensional representations. A lot of which, especially for the case of n-grams, can be mostly zeros unless you do a lot of special, interesting things to them. You have contextual embeddings, which we'll talk about later, and we'll talk about why we need them a little bit later also in future modules. But the same word can be represented in many different ways depending on its context. So we'll probably use the word play, for example. So a play in hockey, which is the best team sport in the world, will mean sort of a sequence of people getting the puck and scoring a goal, for example, whereas going to the play at Neptune Theatre in Halifax, for example, or one of the Mirvish theaters in Toronto, going to a play, watching actors, the word play will have a very different meaning in that context. So the embedding for the word play will occur in a different spot in the text embedding space. That's for later, but for right now we're going to talk about dense word embeddings just to get us on board. So there's lots of good examples of this. Word2Vec, glove, and fastText were among the most popular ones in the mid-2010s, in which every token, every word type, will be a very dense packed vector with a lot of semantic structure and syntax and so on, which we won't talk about too much because this is not a natural language processing course. Let's see some examples. So let's go to see GigaWord. So we're going to explore word embeddings. So here what we're going to do is we're going to see like how do words that are embedded in text space, like how can they be considered to be meaningfully similar to one another? And we'll do that through simple analogies. And we'll see that soon enough, and we'll do this in a two-dimensional PCA space or possibly a t-SNE space. The data set will come from a pre-trained embedding model from GigaWord. So you'll see in the code how to grab it. This is a glove model trained. So glove is just a simple small neural network trained to just basically predict whether or not this word occurs in a number of times in sentences with this other word. So in all these sentences in Wikipedia and the GigaWord corpus, you have all these sentences, and if these two words occur together in the same sentences, then we want these embeddings to be close to each other in space. There's Word2Vec, which is more about taking a sequence of words and trying to predict which word occurs in the middle of this sequence. There's alternate versions of all of these models. Again, we don't need to get into it. We're basically just trying to make, unsupervised predictions of whether a word occurs or not in a context, and we'll make that prediction using neural networks, and we will train them using samplings of various kinds, and we'll train it in such a way that we'll want the vectors that we produce in the embedding space to carry meaning in a way that I've alluded to a moment ago. So these models, we're not going to train them in this module, thankfully. I mean, otherwise making these slides would have taken forever. We're going to just reuse them, so we're going to grab them. You can see this link over here to learn more about GenSim. This is the library at PyP. So this is what we're going to be using. I want to highlight this, though, because you're probably going to download all this code and try running things yourself. Normally, when you've encountered new libraries like Torch or Torch Vision in previous modules, you just went to the command line and typed in pip install Torch Vision or whatever, and it worked fine. You'd expect pip install GenSim to work, and it kind of should, but on both my Mac and my far superior Linux machine, this did not work, not even in Linux. So I had to, in both of those cases, use conda install -c conda forge GenSim to get it to work. So this assumes that you're using conda, which you probably should anyways, but again, in order to run these exercises, you might have the same situation as me, and so if that's the case, use conda instead of pip for GenSim, the GenSim library in particular. So here is where we're going to load things. Nothing fancy here. We're going to be using PCA in a moment. GenSim, yeah, so it's not so optional actually, and this doesn't work, so I should fix this comment. But yeah, we're going to call GenSim downloader, because we're going to call it API for now. So from this API, we're going to load this glove wiki plus GigaWord model. This model, again, was trained on Wikipedia and GigaWord, and given text, it will produce 50-dimensional embeddings. So the D is 50, and these are textual embeddings. So I'm going to have a handful of words that we handpick based on precedent. There's lots of examples of people pushing in king and queen and man and woman and so on to these various different kinds of models. And these are our words, which is just a sequence of text. And here's where we take our words, we'll pass them into glove for each of our words in this list, and then we will produce vectors for them in a data frame and then just show them to you. So again, I mean, you can play around with this a lot. This is easy to play around with. It would be very easy for you to just add additional words in this list that you might be curious about, so I'd really encourage you to do that. And similarly, you might want to see this GenSim library, using the link I mentioned a moment ago, what other models exist that you can play around with here. So go ahead and do that. But for the moment, given this particular model, which has 50-dimensional embeddings, and the particular words I've chosen, here's the embeddings. These numbers won't mean anything to you. So king having this first dimension being 0.50451, and its second dimension 0.68607. That doesn't mean anything to you, but these numbers somehow, I claim, are encoding information about what a king is and the kinds of context in which the word king occurs. Similar for queen and man and women and so on. Okay, so these are just representations in some space that represent these words. We can visualize them. So why not just take our PCA and we can say I'm going to use two components, because humans can kind of visualize in 2 dimensions. And we will fit a transformation and then just pass our words into this transformation. So again, these numbers, like in a table, might not mean anything to you, but putting them into a little image over here, now we can start to see like real representations of these words. So this is fortunate for us that things worked out well for us, but here's a principal component 1 and principal component 2. And we see words like Paris, France, London, England, king and queen, kind of forming a little bit of a line over here on the left. And then on the right, we have words associated with people: engineer, nurse, teacher, doctor, woman, and man. I mean, we're taking lots of shortcuts here, so I'm just using PCA to throw these embeddings down into the 2 most useful directions. But already you can see that merely being trained by others on the GigaWord corpus and Wikipedia, that without being told specifically, like, this is what a capital is, this is what a city is, this is what a country is, already the model has learned to embed Paris and France in a similar area of the embedding space. London and England aren't as close as Paris and France are to each other, but they're also kind of grouped somewhat together. King and queen, interestingly, like, they're not occupations, but they might have more to do with this little cluster over here on the right. But kings and queens might have more to do with London and England than they do with Paris and France, which famously decided that they didn't want to have kings or queens anymore. So maybe there's a bit of a separation between Paris and France. Kings and queens might want to stay away from Paris and France. Anyway, again, like this, I found this fascinating when I started learning about neural networks and embeddings within the context of natural language processing. Prior to this, back to the idea of hand-engineered features, computer scientists, undergrads like yourselves, even grad students, professors would have to write up functions to describe Paris in terms of a lot of attributes or features that we'd try to encode manually. And then along comes neural networks, and it's like, you don't have to do all of that. Just get a simple neural network, and just predict it to maybe train it to predict itself. Train it to predict rather words that you're providing it, or words given contexts, and you'll magically learn all these hidden relations that exist in your data. I found this absolutely fascinating when I first saw it. As simple as it might look to you now, it's still like a fundamental concept which underlies even the biggest transformer models we see currently. I mean, this is all well and good. Like, we have a kind of a subjective sort of interpretation of this, but as I think I might have mentioned previously, like, there's danger in doing what I just did, because I come with my own preconceived biases. Like, I want to see patterns. The distance between king and queen in Paris and France, I literally just came up with on the fly as I was describing this. And that's dangerous to do if you want to do science. Like, it gets the ball rolling to some extent, but you need to do better confirmation, something a bit more quantitative. The following isn't exactly quantitative, although we're using numbers, but here we're going to be using like nearest neighbors. So like, what are the points nearest to doctor in my space? Well, the closest word to doctor is nurse, but physician is not far behind. Patient, child, and teacher are words that I've provided that are clustered somewhat close to doctor. But then because I have points and I have vectors, you can do vector arithmetic. Again, I don't want to reintroduce the whole idea of vector arithmetic, but you can obviously add two vectors together to get a third vector. You can subtract vectors similarly, like take the negative of a vector and add those vectors together to get another vector. So you can essentially do arithmetic. So you can take the meaning of the word king, subtract the meaning of the word man, and then add the meaning of the word woman, where meaning is synonymous with embedding or representation here. So here's how I do this, and then I find the top end words that are closest to it. So here's a little bit of code you can play around with yourself. I'm using glove to find the most similar words. So an awful lot is being done for you here. Again, this is not the point of this. Like, vector arithmetic is not the point of what we're talking about right now, but just like conceptually, you know what I'm doing. So if I take the representation for king, remove everything having to do with man, and then have things having to do with woman, what do I get? Well, you actually get queen, which is exactly kind of what we might predict. King minus man plus woman equals queen. That's fantastic. You get some other things which are a bit odder, right? So if you take an idea of a king, remove his manhood, add womanhood to that representation, you get something close to a throne also. Prince is there, daughter is there, Elizabeth is there. So again, Queen and Elizabeth might have a strong amount of correlation, which is why she shows up. But there are other Elizabeths in the world than the late Queen of England and Canada. So anyway, you get what's going on here. This is a kind of an interesting sort of additional evidence that all of these embeddings aren't just producing points that are close to each other, but there's like relations of multiple points that all kind of hang together in more complicated ways that we're observing here. One thing that I wanted to put in that I did not put in here is that not only is like semantic meaning of words preserved in this space, but you can also get grammatical or syntactic relationships preserving. So in other words, you get things like slow is to slower as fast is to faster, and slower is to faster as slowest is to fastest, right? So the arrangement of the embeddings or the vectors for those words representing concepts and their relative forms and their superlative forms all kind of fall in a predictable pattern. So not only are you learning something about meaning, you're also learning something about grammar and what we call morphology, how words change, simply by just predicting words. Again, not to emphasize that, how fascinating that is too much. So these analogy results are helpful, and to a large extent we seem to be falling on things that kind of match what we'd expect. So king minus man plus woman should be queen, and there she is. But why is throne so close behind? Again, there's no silver bullet in machine learning. There's going to be some weird patterns like this. Why are they occurring? Are they occurring randomly and by accident? Are they occurring because of biases and statistics in the training corpus that we don't necessarily like noise, like bad noise? Do these analogies represent things that we didn't expect to find, but actually represent something meaningful that we just didn't know about? All of these things can be true and often are in machine learning generally and embedding specifically right now. It's good for a sanity check. You might want to see things like gender things, really like hymns and her hymns, clustering maybe more closely with his than with hers. But we'll see. We'll talk about that in a moment. Do countries cluster close to their capitals or not? Do professional clusters start to emerge? We'll talk about that in a moment as well. So how do we evaluate text embeddings? Well, we can do nearest neighbors. Are they semantically coherent or not? This requires a little bit of subjectivity. We can do analogy tests, like I did a moment ago. Again, like this, it's very, very robust. So we talked about king minus man plus woman, but also Paris minus France. Like the embedding for Paris minus the embedding for France plus the embedding for Italy is really close to the word Rome. And this is what we expect because Rome is the capital of Italy and Paris is the capital of France. But then finally, kind of the meat of the thing is downstream performance. We want to take the embeddings for sentences and then run them through, again, simple little classifiers like k-nearest neighbors, or maybe simple logistic regression, which is our go-to workhorse for the dirt simplest model we can find, and then see if we get good performance. So again, word embeddings by themselves might not capture more complicated syntax than like the simple word relations I mentioned a moment ago. So like sentences have very big grammatical structures, and and they change sentence to sentence. And word embeddings have notoriously not been too good at representing big long-term grammatical relationships or long-term context, just in terms of meaning, like very long sentences. Embeddings like of this kind are good at little short windows of 5 to 6 words, but like sentences that have 20 words or more, meaning sometimes is lost when you're trying to make predictions. So anyway, we're still stuck in the 2010s right now, just to introduce these concepts. Word embeddings for models like GPT and BERT are far better at this, but they're not perfect either. And of course, biases are always a persistent, pernicious challenge. So that's our first example is text. Let's see some vision examples again. So again, we have CNNs, we have raw images. Technically we have a 32 by 32 pixels, but we have like red, green, blue for each of those pixels. We're going to pass this through a transformation, which is a learned function with parameters theta, which is what we've learned in our neural network. And then we can reuse that in linear probes, k-nearest neighbors. We can use it for visualization, and we can even use it for transfer learning to new tasks. I didn't talk too much about transfer learning in this. I was kind of wondering whether or not I should have a formal definition for this. Because transfer learning is sort of a broad collection of concepts, but it more or less refers to the idea of taking a model that was trained on one task, and then maybe stripping off parts of it like we saw in the previous module, and then using the remaining part of that model as an encoder for some other tasks. So like we have a model that was trained to predict the next word in a sequence in Wikipedia articles. You strip off the top of that predictor, use the rest of that neural network, you transfer that neural network to another task, put another head on, train it to detect whether or not this cover letter is a good representation for an applicant for a job, and then you've transferred the model over. So in this example, we're going to use pre-trained ResNet 18, which is again getting ahead of ourselves a bit more. We've previously just used a small CNN. Again, getting ahead of ourselves. Now we're going to use ResNet, getting further ahead of ourselves. Again, just downloading a vision model for some task and then transferring it to the CFAR10 dataset. Actually, like now that I mentioned it, I'd be surprised if this model was not trained partially with CFAR10 data, but we'll find out. So our goal is to use it as extractor of useful embeddings. And then we're going to use these extracted embeddings for doing some simple classification afterwards. So again, CFAR is the Canadian Institute for Advanced Research. This data set, I could have mentioned it last time, was one of the preeminent data sets in computer vision for the longest time. Another example of Canada being the best country for doing AI and machine learning research. It was true 20 years ago, 10 years ago, and it's still true today. So we have 10 classes: airplane, automobile, bird, cat, deer, and so on. And these are images, not to be too redundant. And we're going to work again like we did last time with a small subset, just because otherwise I'd explode my Apple computer, and Linux would handle it just fine, but there you go. So here we're just loading it. Here I'm going to go ahead and use Torch Vision again and Torch Utils data and my data loader. Here's my transforms compose. Again, this is kind of getting ahead of ourselves a little bit. Here's where I'm loading the data set from CFAR. I'm just going to use the test set, so train is false. I want to download it again, and here I'm just using a small subset of it. I'm getting the models, so Torch Vision has this component models to it. So now I'm saying from models, get ResNet, get the pre-trained version true. Again, this could provide warnings for you if you want. If it does warn, pass this argument weights equals ImageNet 1K underscore V1. Actually, if you use this particular weight, this would be from another data set called ImageNet, and that's where this ResNet is trained. Anyway, this is a big model, pre-trained on some data. I think this is pre-trained only on ImageNet data, which would be an example of transfer learning. We've trained something on ImageNet, another set of data. We're going to transfer it to make predictions on CFAR. And here's our model. It's a sequential. It's just a list that we've described in ResNet. So ResNet is our model. We're going to take everything except the end. This is our model, and then we're going to evaluate how well it does on CFAR. This is what our model looks like. It's, again, a two-dimensional convolution, passed through a batch norm, passed through a ReLU, passed through a max pool, and then passed through, again, some other blocks, and then some more blocks, more blocks, more blocks, and more blocks. It's a relatively deep neural network compared to what we've seen previously in this course. This is where we actually extract the embeddings. So we say whether we can use our CUDA device or a CPU as our device. We take our embedding model, which we've defined in our previous slide, cell, and we put it onto the device. And this is where we're not going to do any training. We're just going to take our images from our loader, from CFAR, put them on the device, put them through the embedding model, get our features or representations from the model, which is going to be 512 dimensions, and then we're going to just append them to a list we want so that we could eventually show them in a few moments. So this is going to produce 500, we have 500 images which are passing through here, and then we're going to get the 512 dimensional representations for each of these, which we get from the ResNet model, which I loaded up in the previous slide, or cell. Here they are. Again, we're passing them through PCA just to get two-dimensional representations of this. You could also pass these through t-SNE if you wanted. So here's our first two principal components, which again, 512, Z is 512 dimensions. We squish it even further to 2 dimensions just for our squishy human brains. Here we have labels for each of these. So CFAR10 again has 10 classes, cats, ships, airplanes, and so on. And you can't see too much of the pattern here by looking at these numbers, but you can see them in this visualization. There's a lot of overlap here, but one thing you might notice is that there's a line that kind of bisects these 10 classes of these 500 images. And it's roughly where I'm drawing my mouse right now. Hopefully you can see that. On the left of this boundary, we have trucks in turquoise, automobiles in orange, ships in green, and airplanes in blue. So all of these are actually all of the vehicles, all of the human-made vehicles are on the left of that line. And on the right of the line, we have dogs in kind of, I want to say gray-brownish, frogs in pink, horses in gray, cat in red, purple deers. So we've already bisected as animals from non-animals. And again, there's nothing, like ResNet was not trained in order to do this on CFAR, but we've automatically, without having to do any training on CFAR, we've already gotten the separation of human-made, like images of human-made things from images of animals, which is great. Now we can do some learning. So now we can take our train test split of our data. We can get our k-nearest neighbors classifier. We can take 5 nearest neighbors. Again, this is using a spelling mistake that sklearn has, but you have to spell it without the U. We fit this k-nearest neighbors classifier, we make our predictions, and then we get our classification results. Our validation accuracy on ResNet embeddings is at 0.6, like 60%. Not great, but not bad. We have a very simple classifier. Like k-nearest neighbors is, again, I assume you've already seen this in another class. Like I'm teaching this to my first-year students. You know, it's the simplest possible classifier. It already produces real, like, goodish embeddings given it produces good performance on classification given embeddings that have been trained previously on a large amount of data. If the embeddings are good, even a super trivial model should get decent accuracy, which it kind of does. Again, the baseline would be 10% with this random guessing if I hadn't learned anything. And again, I didn't have to do anything iterative here either. Anyway, so you could go ahead now, and I go ahead, if you wanted to replace my k-nearest neighbors on this slide with something a bit better, you know how to produce logistic regression now, so you can replace this classification with logistic regression to see if you do any better than this. You know, apply regularization, do all the good stuff we talked about in this course. Go ahead. So evaluating image embeddings now. So the first example was text. Now we're doing image embeddings. Again, you can do linear probes for accuracy. So given a frozen embedding model, so we're not training that big fancy ResNet model anymore. We're just going to train a simple linear classifier on top and see how well we do. We saw that we do fine on it with k-nearest neighbors, so that's a good indication that the embedding model is good. We could do other things. We could do retrieval metrics. So you could take a query image, so take an image from our test set in CFAR, embed it into the representation space of the ResNet model we got out of GenSim, take its 5 nearest neighbors from there, or produce new images automatically if you can do that, and then qualitatively look at them and say, well, does this GenSim model using ResNet produce images that are similar to this new image I've provided? If visually, like an image of a dog from CFAR embeds into a space similar to images of dogs from ImageNet, and that's a good sign that the representation is doing a good job. And then you can do this visually with visualization checks like we did a moment ago. You have a couple of tools you have at your disposal. Again, nice clusters doesn't mean you have proof of generalization. I mentioned before that the rationalization I was doing in the text space with man and woman and king and queen, clustering in what appeared to be similar might be an example of me using my human biases to see patterns that might not actually exist or might not generalize to your downstream task. Overfitting can still occur. Even if these visualizations are pretty, it doesn't mean that they can specialize well, so always be wary of that. So finally, in summary, I want to mention graph embeddings. We might come back to graphs later, but again, there's not too much time in this course, so we won't get into it too much, but I'd be remiss if I didn't, it would be remiss of me if I didn't mention them. So graphs are often represented as vertices, points and edges between them, sometimes directional edges. So in a machine learning context, nodes can represent users, patients, products, research papers, proteins, and the edges are all the relationships between them. So users like friend groups on social media websites, products, how they're often bought together, papers, are these research papers often cited together, are there protein interactions or drug interactions, so there's relationships between these entities that we have in our graphs. And these graphs are often represented by adjacency matrices in code. So again, we want to have a function that takes graphs and in terms of vertices and edges, there should be a comma E here, and produces, actually no, sorry, it takes the vertices, so I care about those things I'm trying to represent. I want to learn about users, products, papers, and proteins, and I have information about them through the edges that connect them, and I want to transform information about users, products, papers, proteins, etc. into these d-dimensional embeddings. And why do I want to do that? Well, I might want to do some downstream tasks. I want to classify nodes. I want to classify this drug as being useful to cure or at least mitigate against a particular kind of disease, and I know information about other drugs similar to that drug. You might want to automatically cluster and identify cliques or communities for some downstream task. I want to stay away from machine learning tasks on social media for reasons that might be obvious. And you might want to have recommendation systems and so on. So here's where I cite some of these papers. So Deep Walk and Node2Vec are kind of foundational papers in learning embeddings, vector representations of graphical data. This involves taking random walks in the graph, treating them kind of like sentences in our previous conception, and then doing Word2Vec style training on node sequences. Graph neural networks are also extremely popular. I have some textbooks behind me, behind the green screen also, about graph neural networks that basically iteratively aggregate features in neighbor space and produce updated node embeddings. Groups of my research students are also working in this area. It's an active area of research. Because you have inbuilt relationships already known unambiguously between concepts in your data, in your graphs, graph neural networks have all kinds of, it's a shortcut to useful embeddings that carry useful relationships in them. So common strategies that work, whether you're using text or images or graphs, Downstream tasks are always helpful, so you're often going to be doing classification or regression. So just passing embedding vectors as inputs to arbitrary classification models or regression models, like we've seen countless times already, well, not countless times, but often in this course, is a good way to test whether or not that embedding is useful or not. We saw it in both vision examples and text examples. Looking at neighborhoods, like we saw especially with text, and I talked about briefly in images, are there semantic relationships or structural relationships that are meaningful? Are the clusters that we're seeing formed meaningful? Again, if you're dealing with clusters, you can use silhouette score or some of these other scores that you've previously seen in other courses. And then do some robustness tests, which I maybe might assign more to you. I might try to put that into the notebook for this very module. But yeah, like adding noise and slight augmentations to the data to see whether or not you have equivariant or invariant representations is something we should probably explore. And then generally always ask, like, what are this embedding space going to be used for? Like, what do I care about doing this embedding in the first case? On which data distribution, for whose benefit, and whose detriment if we don't take extra care. Speaking of which, there's lots of papers here you should check out. Embeddings can learn bias and stereotypes of various kinds, and there's some famous papers here, which I am not citing here. I should add that also. Anyway, there's I previously showed you, king minus man plus woman should point to a space in the embedding space close to queen, but there's a famous paper that shows that if you take programmer minus man plus woman, and the space around that is homemaker. So, it tells you something about the stereotypes that exist in between gender and their roles in society or their roles in work. Okay, so all of these embeddings that I'm learning just from data, just making predictions on data, can build in racial, religious, cultural, gender, and other types of stereotypes, which would be faulty, right? Like if you, again, back to the original example of taking lots of cover letters and CVs from applicants to a job, and then embedding them into like a d-dimensional space, and then finding which vectors are close to each other. Well, if we've learned that men and women are different than one another based on ancient historical data, then it'll offer up jobs, high-paying jobs for surgeons and machine learning scientists to maybe men who have been predominant in those areas in the distant past, and it might promote jobs in stereotypical female jobs like nursing, for example, or homemaking. That isn't just an example off the top of my head. That's like an example that, other companies, some of the major companies from the United States have been found liable for making exactly that kind of faulty prediction. Whether or not it was on purpose, who knows? But even them, with all the resources, failed to do what you can do now with your advanced knowledge to solve these problems. Image embeddings are the same thing. In fact, one of my postdocs is working a lot on image representations related to skin color and gender, and how hard it is to disentangle those concepts from images of faces, for example. Privacy and leakage. So here's some foundational papers on privacy and leakage. Embeddings might also encode information about sensitive attributes or memberships of individuals in the training set. This isn't a course on responsible AI. Dalhousie is close to like we're thinking of adding a new fourth-year class on responsible AI. Even people, if everyone's lucky, people in this class might be able to take the fourth-year class on responsible AI. But there's going to be a lot more information about how privacy is circumvented and how personal information is leaked in a lot of the kinds of models we're talking about today. Fortunately, there are lots of mitigations. I cite a couple of, actually here is the paper I was worried about a moment ago, Man is to Computer Programmer as Woman is to Homemaker. I should provide a link here. That's another oversight, but you can search for this online. This is a famous paper that shows the kinds of stereotypes that exist in these kinds of models. But there are ways to circumvent it. You can perform bias probes, so just simply look for bias in the first case. There are ways to embed things in a way that that separate out. Actually, I cite two excellent pieces of work here by Chen et al. And Balapaganan et al., which are some of the papers in our group that found ways of identifying bias in the latter case and actually circumventing it in the former case. This paper in particular, so anyways, I'll point to them in a second. You should check them out. So just because these models can produce biased embeddings doesn't mean we can't apply methods to debias them. I thought I'd remove this slide, so I'm just going to skip over it. Here's our quick check. Here's our references. Here's one of the first papers I mentioned, or the papers I mentioned previously. This is more about explanation actually than mere bias, but there's a lot to do with bias in there as well. So check out these papers. They're really amazing. This is work by some of my colleagues at the Vector Institute. This is a foundational paper also, which you should check out in particular. As always, thanks so much. See you next time.